This evening, our member, Spencer Martin, who is a high school student, he's a rising junior in high school, is going to give a presentation. He joined the club about a year ago. He is now our communications intern for our club, and then he's in charge of updating Instagram and Facebook, etc., to give information about our club, to announce the weekly presentations that we have. And at this point, then, I would like to turn this over to Spencer. Okay?
All right. Thank you, Mary.
Paul, we're going to turn out the lights, so.
All right. Thank you, Mary, for the introduction. So, my name is Spencer Martin. I'm a rising junior, as Mary mentioned. I attend Scotchlands Fanwood High School, and I've been a member here for about a year now. So, here's my presentation about the standard model of particle physics. So, I'm not sure how much you guys know about it, but you'll learn a lot. All right, so a quick outline of what we'll talk about. Here's an atom. Talk about that too. So introduction, historical backgrounds, the atom, which is right here, matter particles, antimatter, Feynman diagrams, fundamental forces, the Higgs boson, quantum field theory, particle accelerators, limitations and challenges of the standard model, and the future. Looks like a lot, but it goes by pretty quick, I promise. All right, so a quick introduction about the standard model. It's a theory that describes the fundamental forces and particles of the universe. So before we have planets and galaxies and stars and everything like that, it starts with atoms. And in atoms, there's even smaller things, which are subatomic particles, because subatomic atom. So that's what an elementary particle is. It's as small as it can be. So an electron, you can't cut in half. Cut in half, nothing happens. It's not possible. The field of particle physics, it helps us to understand the Big Bang, mostly, and how everything here came to be. So it's still an ongoing work in progress. There's always science being done, always new discoveries being made. So for that reason, there'll be some things that I mentioned that won't be completely finished or completely understood. For example, gravity. All right, so quick historical backgrounds on the standard model and the history of physics. So in 1802 to 1804, around then, that's when the Dalton atomic theory came along. And that basically said that let's say you have a block of iron. It says that there's atoms inside of that block of iron that make up the block, and they're each identical, except there's different types of atoms that make up different elements, which was correct. But then, 1897, that kind of changed a lot. That's when the electron was discovered. So by discovering the electron, that proved that the atom wasn't the smallest thing there is. That meant that there's things smaller than the atoms. And since they discovered that the charge of the electron was negative, and when I say charge, that's like a battery. So if you have a battery, positive end, negative end, or a magnet, a positive and negative pole, same idea with that. So electrons have a negative charge. So they knew, oh, there has to be something in the middle. There has to be protons. And that's what the positive nucleus is made of. There'll be a visual of this after, so you get a better visual explanation. Then through this time period, through 1932 to 2000, about then, there's a discovery of a bunch of different types of particles. So there was neutrons, neutrinos, muons, tau, W and Z bosons, beginning of the quarks, which I'll talk about that later. And then 2012 was the discovery of the Higgs boson. If any of you were reading the news around then, people were going crazy because they thought it was the God particle. No one knows what that means, but people were excited about it. So a couple more points here. 1897 was the electron. 1905 was the photon, which was proposed by Einstein. 1930 was the neutrinos that were proposed. 1936 was the muons. 1978 was the tau, gluons, W and Z boson, etc. A bunch of discoveries over the past 100 or so years. All right, a couple of notable figures in the field of physics. Probably the most famous, Albert Einstein. You all know about him. He's probably your favorite and only physicist that you know. Then Enrico Fermi. He actually has a lab named after him called Fermilab. I met his granddaughter recently, so it's cool to talk to her. Then Wolfgang Pauli, if you guys took chemistry, you'll probably know the Pauli exclusion principle, where two electrons can't be in the same orbital if they spin up. It's two spin up. And then Peter Higgs, he's the one that discovered the Higgs boson, the God particle. All right, so this is as simple as the universe gets right here. So here's the protons. You could picture them as two little balls. They're not really because they're quantum, but they're two positively charged little circle things. And together, there's neutrons, which have no charge. Then orbiting around them with the negative charge of the electrons, which I mentioned before, and the positive charge of the nucleus and the negative charge of the electrons. It keeps the electrons in place orbiting around the positive nucleus. As I mentioned, kind of like a battery, if you put two batteries together or a magnet, positive and negative side, they come together. If you put positive, positive, they repel. So it's kind of like that. All right, so here is, again, is the standard model. I'll teach you a bit how to read it. So all of these things, they're all particles. So the left side over here, these are the fermions, which are matter particles, and then here are the bosons. It also tells you right over here. So there's two different types of fermions. There's the leptons and the quarks. These are the smallest things that there are. The leptons are much smaller. Now, a quick way how to get information about each particle. The number all the way on top is the mass. The number right here is the charge, and the spin is right there. So it's not like they're actually spinning. Like the electrons aren't spinning in circles and getting dizzy. It's just a quantum number. That's how they describe it. It's hard to understand, but it's just an identity, pretty much. So here's the matter particles. Here's the two sections. There's the quarks and the leptons. And I'll talk about the quarks first. So there's 6 different types. There's the up, down, charm, strange, top, and bottom. Not very good names because nothing's really on top or on the bottom. Nothing's pointing up, nothing's pointing down. It's just what physicists choose to name them. So these quarks, they make up the protons and neutrons, and also pions and kaons. So whenever you take a combination of quarks, you put them together, they make hadrons. There's subcategories of hadrons called baryons and mesons. So baryons are what we're familiar with. That's the protons and neutrons. They each have 3 quarks. Fun fact about how protons and neutrons get their charges. So proton is a +1 charge. If you look at the quarks inside, it's an up, up, and a down. So their charges are going to add to +1. So you have an up with 2/3 plus another 2/3 is 4/3, and then minus 1/3 for down. So that's +1 charge. That's how it gets it. Then the pions and kaons, these are mesons, and they only have 2 quarks. There's also tetraquarks and pentaquarks, but they're pretty rare. That's when they have 4 or 5 quarks in them. And there can never be 1 quark by itself because of quantum chromodynamics. I won't bore all of you with that. It gets intense, but there can never be 1 quark by itself. All right, here's the leptons. So first is the electron. Everyone has heard of the electron. Is the electron family, which is just this row across. And then there's the neutrino family, which is on the bottom. The neutrinos are the smallest particles in the universe. It's as small as it gets. There's actually 100 trillion of them going through your body every second. So the sun generates them. So the electron, it's found in the atom, orbiting around, as I mentioned before. The muon is pretty much the same thing as an electron, just a little bit bigger, a little less stable. And they're found in cosmic rays. They're also used in muon tomography. It's kind of like a 3D scan type thing. So there's been research done on the pyramids in Giza where they shoot muons through it and they make a 3D map of the tombs inside. So it's pretty cool to see that. And then there's the tau, which is a bigger version of the muon and electron. So there's the electron. Then there's the neutrinos. The neutrinos have different flavors. You can't actually taste them, unfortunately. But they have different flavors. There's the electron neutrino, muon neutrino, and tau neutrino. You can see how they got their names, just the particle above it. And they're responsible for decay. So back in the 1920s, 1930s, around that time period, there was a big mystery in quantum physics. So when particles were decaying, they would, so carbon-10, for example, when it decays into boron 10, it emits a positron, which is an anti-electron. I'll get to that later too. They were missing something. So it was almost like you have a 10 over here, you subtract a 9, which is the positron, and then you're still left over with 1. So there had to be another particle, super tiny particle, in the decay. And that was the neutrino. So super tiny, but still there. And this huge gold room on the bottom, they fill that chamber with liquid argon, and that's how they detect neutrinos. Since they're so tiny, they rarely interact with matter. You need, I think it's 200 miles of lead to stop them. But they rarely interact. That's why you don't feel the hundreds of trillions of them going through your body every second. All right, antimatter. So antimatter, it sounds like something sci-fi. Kind of is. I think it probably was at some point. If any of you have seen Mr. Peabody and Sherman, there's the one scene where there's two Shermans and they touch each other and they go into like a whole world. That's pretty much what it is in real life. So it was discovered by Paul Dirac. He's known as being a weirdo, believe it or not. That's his equation that predicted the existence of antimatter. So he was just trying to describe how electrons float around, how they do their thing. But he got two outcomes, kind of like a plus and minus. That meant there had to be another type of electron, and he was right. So we call the positron a positron because it's an electron with a positive charge. The other antiparticles are not named too well, but they have the same mass, same spin, but a different charge. So an electron and a positron, they're basically the same thing, other than their charge. So there's not just anti-electrons or positrons, there's also anti-quarks. So there's 6 quarks, as I mentioned before. It's actually 12, because each quark has an anti-quark, and it's the same thing. So for an up quark, its charge is 2/3. An anti-up quark, it would be negative 2/3. And they also make up anti-hadrons. So here's an anti-proton, anti-neutron. And anti-proton has a -1 charge, and a neutron still has a 0. So it is. And then antiprotons are written as that, with P with a little bar above it. That's why they're called P bars. So probably won't hear that too often, but they're called P bars. So whenever you see a line above something in the context of particle physics, that just means anti. So it's an antimatter particle. All right. So we've covered all the matter particles. Anyone have any questions about that so far? I'll take that as a no. All right. So this nice guy over here, this is Richard Feynman. Some of you who were around during the Challenger disaster, you might know his name. He's the one that was on the Rogers Commission, and he figured out that it was the O-rings that were the issue. But other than that, he was a really famous Nobel Prize-winning particle physicist. And he's known for his strong New York accent and his easygoing explanation of these super complex topics. So one of the ways he explained these crazy things to people were by Feynman diagrams. So it's what it is. There's a space axis and then time. So what this one is saying, there's an electron over there where it says E-. That's how electrons are represented. And another electron over here. This arrow is showing that the electrons are coming towards each other. Except as you follow the time, electrons are coming towards each other. And once they get here, they exchange a photon, which is a light particle discovered by Einstein. And then after they exchange the photon, they go their separate way. So that's called electron scattering. That's the specific interaction. But up before this, before Feynman created these, there was super complex equations, nothing like this to explain it. So the only important things about Feynman diagrams are the input and the output. So if you have 2 electrons going in and 2 electrons going out, that's all you really have to know. Anything can happen inside this box right here. So you could have the exchange of a photon. You could have exchange of 2 photons. You could have a photon being emitted and then reabsorbed by the same electron. You could have this whole thing where there's a bunch of annihilations and weird things going on. But none of it really matters. Just the more particles and more interactions that are in it, the less likely it's going to happen. So that's why this is the main example for electron scattering. So here's another Feynman diagram. This is another quick example. Here's a positron because the E+, an electron with a positive charge. Then there's an electron over there. When they come close to each other, right where that arrow is, they annihilate. So that basically just means they touch each other and then they disappear and emit something else, which are the two photons up there. Photons are light particles. You can't actually see these interactions. They're super tiny. If this happened like in your hand, you might feel a little shock, if anything. You probably need like hundreds of thousands or trillions even to feel a real pain. And also the reason that the positron has an arrow going this way, it doesn't mean the particle is traveling this way. That's just how antimatter is represented. Still going that way as time goes on. And the reason annihilation is so important is because when the Big Bang first happened, the universe wasn't created equal because we're all made of matter, not antimatter. We know that for sure. So picture this as 11 or so matter particles. And then there was also antimatter. So when matter and antimatter, they touch each other, they annihilate, don't exist anymore. So boom, they're left with matter. So there was a super tiny imbalance right when the Big Bang happened. There was a little bit more matter, and that's what everything around us is made of. So all the antimatter is gone, most of the matter is gone. We're just a little bit of matter. So that's kind of how we got here. Here's more Feynman diagrams. They get kind of complex, but still better than the equations. I won't explain the whole thing. Right, so here are the fundamental forces of the universe. So you all probably know gravity and maybe electromagnetic force. That's what light is. For any of you astronomers, that's what spectroscopy is. That's using photons and the electromagnetic force. So the different forces are the strong force, weak force, electromagnetic force, and gravity. And they each have their own particle that mediates the force. So if you track the force down into a single point, it's a single particle. So for the strong force, it's the gluons. And the gluons are very appropriately named, so I'll explain that once I get to that. Then for the weak force, there's the W and Z bosons. Electromagnetic force is the photon. And the gravity, we don't know. So that's one of the biggest problems with quantum mechanics and general relativity. We're still trying to find a way to describe gravity on the standard model. So each of these other forces, it has a particle that works with it, but gravity just doesn't. So we're still working on that. All right, so about the strong force, it's mediated by the gluons. The gluons are what hold the protons and neutrons together. So inside the quarks, inside the protons and neutrons, there is the quarks, which I mentioned before, and the gluons holding them together. That's why they're called gluons. They literally just glue quarks together. It's gluing on. And they also hold together the protons and neutrons inside of the nucleus. Because when you have all these positively charged things, if you have a positive magnet and another positive magnet, they repel each other. The neutrons are neutral, so they don't really matter too much. I guess they are matter, so they do matter. But yeah, so they keep the positively charged protons together. All right, now is the weak force. It's mediated by the W and Z bosons. Not very good names, not as good as the gluon. But they're responsible for carrying out decay. So when you have a super large unstable nucleus like uranium-232, it decays into a smaller, more stable one and emits some type of particle. It could be an alpha particle, beta particle, it could be a light particle. Just depends on the type of atom and the type of decay that it goes through. But the bosons, they help it undergo that process. All right, then the electromagnetic force, mediated by the photon. Here is the visible light spectrum right there. This is just magnified. There's also the other different types of light, which as astronomers, I'm sure most of you have heard of. There's the AM waves, the short waves, TV, FM. Those are all different wavelengths. So electromagnetic force, it also creates magnetic fields. So if we didn't have that, we'd probably all have really bad sunburn. So here's the Earth right there. And this big jellyfish type thing, that's our magnetic fields. And it protects us from all of the particles that the sun's shooting at us every second. So yeah, if we didn't have that, it would be a big issue. All right, and then gravity. Still don't know the particle, hasn't changed in the last couple slides. Einstein wins again. He was pretty against the whole idea of quantum mechanics And what quantum mechanics is, it's just probabilities. So instead of a particle, it's more of a wave. So picture a wave of probability. The particle could be anywhere in that wave. So if it's like a parabola where it's, picture like a rainbow on that screen, chances are the particle is not going to be here where the probability is super low. It's more likely to be up there. Still a chance that it's down here. So Einstein didn't like that whole idea of not being certain of where a particle is because it's pretty unsatisfying. It's not good not knowing where something is. All right. Now for the Higgs boson, this is the God particle, as people like to call it. It was discovered by Peter Higgs. These were his original papers of his proposal. He proposed it in 1964, and it was discovered in 2012. So it took quite some time. And what it really is, you can't really tell. So that's supposed to be a big grid, a big 3D box, and it's really supposed to represent a field. So picture a soccer field, right? As a grid, kind of. Picture a soccer field in every direction, everywhere, invisible. So we really have fields everywhere in every direction. You can't zoom in with a magnifying glass or anything like that. You can't see it, but it is there based on the theory. So another thing about this, we can't really look at it. It's not experimentally possible to understand. So that's why Einstein was unsure about this whole theory. But for the Higgs boson, there's a field like this in every direction, everywhere, every space, all time, everything like that. So that's the Higgs field. And that's what gives us mass, what gives us weight. So for example, let's say you have a high energy particle with no mass. That could be like a photon. It's going super fast, the speed of light, fastest it can go. So it has no mass and super high energy. It stays on top of the Higgs field and has no mass. That's why it's weightless. But if you go down to here, if this is a quark that does have mass, it doesn't move too fast, it doesn't go the speed of light. Only thing that can go the speed of light is light. So it drops down in the Higgs field, and that's kind of how it has a mass. So the discovery of the Higgs boson, it was discovered at CERN, which is the European Council for Nuclear Research. It's all jumbled up in order because it's in Swiss or whatever they speak there. It was discovered using these two super big detectors. So what a human is in comparison. You see that blue bridge type thing over there? You could stand on that and the railings would be up to here. So that's kind of how big that machine is. That's the ATLAS experiment. And here's CMS. So together they made billions of collisions per second, trillions of data points per second, and they used all that data to prove that there was a particle there. And after doing that, they had a party at CERN. All the physicists were super happy. This was from July 4th, 2012, when they first announced the discovery of the Higgs boson. All right, so now we've pretty much covered all the particles here. Any questions about that?
Can I ask about
Yep.
the CERN? Was it just one particle that they found for Higgs boson?
No, it wasn't one particle. They created a bunch of different particles, if that makes sense.
Yeah.
So they had trillions of different collisions every second, and they would use the different decays to prove that the Higgs was there.
Oh.
So the Higgs decays, and it could decay into like a W boson and a Z boson. If they keep detecting a certain pattern that it's there, that means that they discovered it.
Thanks.
Any other questions?
And the collisions, were they between electrons or?
They were between a bunch of different particles, mostly ions, so lead ions, because they're super heavy and they have a lot of energy, and they could create a lot of new things. Good question. Anyone else? All right, keep going. So this is probably the hardest part of the talk, but it goes by quick. So here's quantum field theory. So as I mentioned before, there's fields in every direction, everywhere. So for now, we'll just picture a field like this with these little bumps. These little bumps are virtual particles. So they're not actually there. So picture this field, it's taking energy from over here, this blank white space, the vacuum, which is the vacuum of space and everything. So it takes a little bit of energy to get there, but not enough to become a real particle. Once it becomes a particle, there's these big spikes like that. So these big spikes are the real particles. Everything else is a virtual particle. Now, as I mentioned, there's fields in every direction, everywhere. So each of these could be a different particle. So this could be an electron field, this could be a muon field, photon, gluon field, a top quark field, fields for anything. So here's the Feynman diagram from before. This is an annihilation. And what the Feynman diagrams are really good at doing is explaining quantum field theory interactions. So it sounds super crazy, but all it is the same thing as a Feynman diagram. So when you have two electrons hitting each other and going away, that's just an easier way of explaining what happens in these fields. So here's an annihilation, which I talked about before. That's when there's a positron and an electron. So when they come together, they do their annihilation thing, and they give off two photons, so two light particles. So that happens when there's an electron field and a photon field, because those are the two particles that are involved. First, there's an electron. Then there's a positron. So antiparticles, they don't have their own field. They're not really down, but when you put a picture of it, that's just how we represent it. So for our purposes, it's all right. So once these two particles come together, that's where we're at the stage right here. They come together and they annihilate. Once that happens, they deposit their energy into the photon field. So once the photons are there, they then go their separate ways, just like that. So I'll quickly do it again. So you have the two electrons in different places. They come together, they annihilate, turn into photons, and go their separate ways. So that's how to understand a Feynman diagram. So cover all that. That's pretty much all the hard stuff. Now we got the fun stuff about particle accelerators. Here's the Flash. I'm sure you all know how he became super fast, the whole particle accelerator thing. Unfortunately, if you get hit by one, you won't become super fast. You actually won't get too badly injured. There was actually one Russian scientist who got shot in the face with a particle accelerator. He survived and he continued doing physics. The only thing was the side of his face that got hit by the accelerator, it just didn't age. So kind of like a quantum Botox, if you will. So here's the inside of a particle accelerator. Kind of looks like a face where these are the two eyes and that's the mouth. This is the LHC at CERN, the Large Hadron Collider. Large because it has a 16.6 mile circumference, and hadron because the particles it smashes are hadrons, which we talked about. Those are particles made of quarks. And collider because it collides them. So these two parts right here, that's where the particles go through. So they have particles going this way and particles coming this way. So when they go around in circles and circles and circles, they get closer and closer, and then at a certain point, they collide. And that's what happens in the super big detectors, which I'll show you after. So here's the LHC. It's in Geneva, Switzerland. It's the biggest particle accelerator in the world. The particles inside of it travel 99.9999991% the speed of light. So pretty fast. Nothing really gets faster than that on Earth. They've also created super hot temperatures here. So they've gone the fastest and the hottest. It's 2 trillion degrees Celsius, which is about 1 million times hotter than the center of the sun. We've made really hot temperatures here on Earth. That's what underground in the LHC looks like. That blue pipe right there, that is this. So this is inside of that whole casing. And that's where it is. So that tunnel goes 16.6 miles underground. And whenever there's a particle in here going at full speed, it goes around this ring 11,245 times per second. That's how fast it's going. As I mentioned, when the collisions happen, they happen inside these detectors. So these are located at different points along the LHC. So this one is CMS. This is my favorite one. It has a cool look. It kind of looks like the one from Spider-Man Into the Spider-Verse, if you've seen that. Then there's the Atlas detector, which is also huge. The closest particle accelerator to us is at Brookhaven National Lab. It's probably about 3 hours out from here on Long Island. It's not as big as CERN. I believe it's 2.6 miles in circumference. Still pretty big, but not quite as good as the one in Geneva. All right, so the limitations and challenges of the standard model. Gravity, still can't figure out a way to get a particle for it. If there was a particle, we'd call it a graviton. That's just the predetermined name if it does happen. But gravitons still don't exist as far as we know. Dark matter and dark energy. So the thing that holds galaxies together, we think, whenever we look up at a galaxy, we'd expect it to be spinning super fast because our galaxy, for example, we're a spiral galaxy, a barred spiral galaxy. So we're spinning super duper fast. We think that these stars would just shoot out from our galaxy, but there's something holding them together. And we think that's what dark matter and dark energy is. So anything dark, that really just means we haven't discovered it. They try to make it sound scary. It's really nothing crazy. Neutrino oscillation. So as I mentioned, the neutrinos have different flavors. There's the muon neutrino, electron neutrino, and tau neutrino. So as they travel from the sun, for example, it will start off as an electron neutrino, and then over time, it will change. It can become a muon neutrino or a tau neutrino, or stay an electron neutrino. Still don't know why that happens, and that's one of the things we're trying to figure out. The neutrino mass, as I mentioned, it has a super tiny mass. But some equations, they say that they're massless, but we know that's not possible because it wouldn't solve the issue of decay. So that's another thing that physicists still have to work out. Any new particles? There's always new things being discovered. So the most recent one was the Higgs in 2012. And then gravity's effect on antimatter. So here's two experiments. Dune over here, the deep underground neutrino experiment. It's kind of a silly name, but what it is, they recently finished excavation. They dug an 800-mile tunnel between Chicago and Idaho, I believe, or Iowa. And what they're going to do is shoot neutrinos underground that distance to see if they change flavors. So if they do change flavors, then they'll understand how we can really understand the whole process. And then G-bar, this is at CERN in Geneva. And this is measuring the effects of gravity on antimatter. So since we have, let's say, a positron and electron, we know electrons fall to the ground when you drop them. We don't know what happens to a positron. It could just be the exact same, but that's why we're experimenting. That's it. Any more questions?
Yes, I have a question.
Oh. Go ahead, Bonnie.
Okay. You referenced Sherman and Mr. Peabody.
Yep.
Those cartoons are not your generation. How do you know about them?
Well, there was one movie, I think 2013-ish.
Yeah.
Something like that. So I saw it then.
Uh-huh.
Okay, we saw it when it was first run.
Great job, Spencer.
Thank you. All right, there's a question in the back.
Yeah, so I'm not sure if you're aware, but currently there's a new quantum lab that is being built in Princeton University, and I'm also involved with another project in New Brunswick now for Nokia Bell Labs that is in progress, that is moving to New Brunswick, and we're building a quantum lab. Can you explain a bit more? Do you know what's happening in a quantum lab, or the tests that's happening in Princeton or in Nokia? Any idea?
Well, there's different things going on in each lab. So there's the Princeton Plasma Physics Lab, if that's the one you're talking about.
Yeah.
So that's where they have fusion reactions, just like what happens in the sun. So fusion is when you take two atoms together, smash them, it creates a lot of energy. So I'm sure you've heard of fusion. But that's what they do at Princeton, and they try to make a self-sustaining fusion reaction because a lot of people think that that's the new way energy is going to be because it's sustainable. You put in a little bit of energy, well, a lot of energy, but it gets going and it doesn't stop. At Nokia Bell Labs, they have a lot of things going on. That's mostly like cell phone technology and radio waves, things like that. Yeah, a lot of cool stuff here in New Jersey even.
That's certainly. People are not aware of it, but I just want to make sure the crowd is aware.
Yep.
Quite a bit of research going on.
I drive past Bell Labs almost every day, so
Yeah.
it's fun to see.
Well, now it's moving to New Brunswick in 5 years, so it's going to be brand new building. A lot of labs and quantum labs.
Yeah, it's a cool campus they have.
Yes.
Any other questions?
Got one.
So that maybe there's a particle for a gravity particle, or they don't know,
They're still not sure about
they're
that.
not sure.
I'll explain later why.
That's
Any- Yep. Yeah, Cliff.
very good talk. I enjoyed it very much. And
Thank
I'm
you.
wondering what you think about the sterile neutrino. I heard a talk online the other day, and an astrophysicist had his favorite candidate for dark matter is the right-handed sterile neutrino. It's a very heavy particle, and its pair is the left-handed sterile neutrino, which is massless. So have you heard about that? And where would you put it on the standard model?
A little bit. I've heard some theories like that, similar to like supersymmetry, if you've heard about that. So people are creating like different standard models around supersymmetry. Supersymmetry is basically if there's a matter particle, it has a force particle. That's like the same thing in a different universe, kind of. It's the best way to explain it simply. So yeah, there's a lot of people creating theories about that. But I haven't looked too much into it.
And speaking about the guy who got hit by a particle accelerator, we have a particle accelerator in New Jersey. It's Princeton Procure in Somerset. And they have a cyclotron that creates a beam of 250 megavolt protons. And I had a tumor treated with that. And they got the tumor, but now I don't grow a beard on the right side of my face.
That's pretty cool. Yeah,
Where's that located? Is that in Somerset?
where was that located?
In Somerset.
Does he know the street?
Do you know what street?
Yeah, it's what is that? It's off of Easton Avenue just before Route 287 goes by. I think it's Cedar Grove.
Oh, okay.
There's plenty of medical applications like that. There's proton therapy, and then
Yeah,
PET
proton
scans.
therapy, yeah, we built a few of those too across the country, but they're ready to come by. I think that's one of the facilities in New Jersey, proton therapy. Yeah.
There's also PET scans, which are positrons. They put them in your body, they annihilate. Yeah. All right. Any other questions?
One question.
Yep.
What's the purpose of the Dune project? Because I mean, I understand it has to be like a circle that you accelerate particles. That tunnel is straight.
Yeah. Let me just get back to it. All right. So here's Dune right here. Can't really see with the lighting, but it starts off at Fermilab, which is in Chicago. Then there is an accelerator, which is creating protons. And then the protons are then smashed into a wall over here. And by doing that, they create neutrinos. So once the neutrinos are created, that's what travels the 800 miles. So they just want to see what happens as they go over a distance. So the accelerator isn't really too important there. The only thing that it really does is just create the neutrinos. But they need it to be more of a straight line for that.
I see. And that 800 miles, did they accelerate the particles again, or?
No, it's just the tube, pretty much. Yeah, you're still working on it. They actually finished excavating 2 days ago.
Thanks.
All right. Any more questions?
Not
All right. Thank you, everyone.